Okay, good morning. Oh, we got some homework here. Let's see here. Some homework handed back. Gosh. Michael. Ian. Ian. There we go. So last time we introduced the exponential function, and it was the function that is going to be used to describe the stacks of paper, right? Stacks of paper. Why do they grow so fast? What are their properties? We'll do some of that. But the exponential function has sort of the opposite format of a power function. Up here, we saw that the power function, you have the variable as the base, and the exponent is fixed. For an exponential function, the base is fixed, and the variable's in the exponent. The base, and we belabored this last time, it's very important that you understand it. The base, for purposes of this class, in this book, can take values bigger than 0, not equal to 1. Translating that, it can take values between 0 and 1, non-inclusive, or strictly greater than 1. So there are two intervals in which the base can take its values. 0 to 1, bigger than 1. We did these. The graph on the right is, notice, the base is 1/2. That is between 0 and 1. If the base is between 0 and 1, the graph of an exponential function is going to have a general down ski slope shape. All right. If it's greater than 1, which is the other place the base of an exponential function can be, it's going to go up. You have exponential growth on the left. On the right is commonly called exponential decay. But we're going to get into that later. You have to remember those now. Another thing to remember here is up here. 1/2 to the x is 2 to the minus x. So if you run into a base to a fractional power that's base to a negative power, keep in mind the rules of exponents. And we're actually going to, there's actually an exponent review slide coming up later. All right. We graphed the function of those stacks of paper there. What are the properties of an exponential graph? Again, on the right, you have a between 0 and 1. On the left, you have a greater than 1. Those are the only two intervals in which the base can take its values. And if it's bigger than 1, it goes up. Between 0 and 1, it goes down. It has a y-intercept of 1 in each case. All right? 1 in each case. All right? Get those here. That is a big fat Greek 1 there. And it is a 1 there. All right? The reason why is that base to the 0 power is going to be 1. So if you have not, if you're rusty on your rules of exponents, and we have a slide coming up, it's kind of a review slide. I'm not going to cover them. I'm going to use them, but I'm not going to cover them. You need to go back and look at those. Some of the properties, x-axis is a horizontal asymptote. In the negative direction, in the case of a bigger than 1, in the positive direction, the positive x-axis is the horizontal asymptote for a between 0 and 1. Domain is all real numbers. You can stick any number in. No numbers are excluded. All exponential functions are one-to-one, and that's what those horizontal green lines depict. They're all one-to-one. All of them pass the horizontal line test. Ergo, all exponential functions have an inverse, and that inverse is called a logarithm, and we're covering those next. But right here, the last one, error. All exponential functions have an inverse. This is all review from last time. We graphed those, did steps, had some homework last time. How'd that go? We're going to cover this little exponent right here. It can be a little bit tricky. We've done them before, but you've got to know your transformations, right? The last section we covered of chapter 2 is essential. It came into play in all of chapter 3. It's going to be in all of chapter 4. It's in all of math. And check your answers on your calculator. We just touched on last time the number E when the board crashed. You remember? The number E is another constant of the universe, right? Just like the number pi, 3.14, right? Approximately 1592653589793, right? E is approximately 2.72. It's a number. This number occurs all over the place in the real world. And for that reason, it's called the base also of the natural logarithms. The base of the natural logarithms. We're going to get into that in the next section. All right? What you got to remember are two things. E is approximately 2.72. So you know around where that number falls. The second thing to remember is this slide. To never, ever, ever, never, 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 ever, never, ever, never, ever, 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 never, ever, never, ever, 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 never plug 2.72 into your calculator and then proceed to use it. The reason why is we have a key. This is where we ended last time. Our calculator, in our little picture there, above the LN key is a key called key with e to the x on it. This is what you are to use to raise e to a power. The function on your calculator. Otherwise, on your paper, you can leave it just as e. You can leave e in your answer. Right? Don't plug in 2.72 because we're going to be raising this thing to very high powers, and the error compounds big time. Your calculator keeps 15 significant digits. That's a lot. So in 2.72, it's got 14 decimal places. Let the calculator do the work. It still rounds, but it rounds at the 15th place, right? When we put something into our calculator, we round it at the second or third place. And when we raise that to a power, the error gets out of hand. So here, and we're going to be doing this. In fact, why not? We're going to be going here. Right? Okay. What do you think of some of that? That's what the other calculus, the other algebra class is doing right there on the screen. The business algebra. So if you want e to a power, right? You go second, ln stands for natural log, and you get a little e on your screen. This is if you have a TI-84 calculator. You may get e to, you may see the caret symbol, but most of you are going to get that on your screen. If I want e cubed, put 3 in, there I have it. That is how you raise e to a power. Okay? Don't put 2.72 in, right? And so you see here that over here on the right, e is around 2.72. You see that e to the 1, e to the 2 is about 7.4, right? That is how you raise it to a power. Now, let's do this one here. This is going to help if you had trouble with last night's homework, this will help with last night's homework, although we have done this kind of thing in the past. We're going to graph e to the 2 minus x. Oh, by the way, e to the x is just another exponential function. E to the x. It belongs in your library of functions. It's already kind of in there, right? Okay, let's do this here. We're going to start off with a plan. Step 1, we're going to take a entry from our library of functions. Y equals e to the x. Now you remember in these, and the reason why I say this is that this has been messed up. This was messed up on the last test. It's messed up, period. When you graph these, I highly recommend doing 1 transformation per step. Don't try 2. Can you do it with 2 if you know what you're doing? Yes. But it is inviting mistakes to do 2. All right? So now I need to turn e to the x into this. E to the x into this. Now, what path should I take? Well, I have a negative in front of the x there. You might do that, right? You might make e to the minus x, so you do 2. This is one way. There's more than one way. Y equals e, and you substitute negative x in for x, and that is what kind of transformation? Last time Alejandro got it. Reflection. It's a reflection about the vertical axis. So this is a reflection about y-axis. Thank you for that response. Now here is the little bit tricky part where last night's homework answer may have given you a difficulty. How do I turn this into that? Well, what do I need in the exponent here? I need a 2. Right? Don't write down what I'm about to do. Or if you do, be prepared just to cross it out as being the wrong way, okay? The wrong way is this. Wrong. The wrong way would be to do this. Y equals e 2 minus x. Why is that wrong? Well, you look at it and you go, well, I have 2 minus x here, and I have 2 minus x there. Okay? The question is, which transformation is that? What kind of transformation if I put a 2 there? It isn't one. This is not a transformation. If I just stick a 2 there, it yields an unpredictable result. All right, if you just stick a 2 there. So I'm going to say unpredictable. Not a transformation. I'm going to call transform, okay? All right, so don't do that. Don't do that. That's wrong. All right? What do you do? What do you do? I need to, what are the allowable things I can do for x? I can substitute in for x, right? I can substitute in. And if I substitute in for x, it's going to do something horizontal. Okay. For example, if I substitute in 2x for x, it's going to be a horizontal compression. For example, That's not what we want to do. But what we need is watch this, y equals e to the minus something, put parentheses there, and I want that minus something to give me e to the 2 minus x. That's what I want it to be. I'm allowed to substitute something in there. What do I have to substitute in there to get 2 minus x? I'll tell you what. What I have to substitute in that blank space to get 2 minus x is the negative of x minus 2. People problem. Only at your college. What do I need to substitute in this blank space to get 2 minus x? I'll tell you what I need to substitute into that blank space to get 2 minus x. It's going to be the negative of 2 minus x, which is x minus 2. All right? So follow that logic. That's what you had to do in last night's homework. So the negative of x minus 2, distribute that negative, gives you a positive 2 and a negative x. All right? This is where you absolutely needed your transformations to be, that blade on your Swiss Army knife needs to be sharp, well oiled. Now, this is a transformation. And I told you it was going to be something horizontal, right? So this is going to be a horizontal shift. Left or right? It's going to shift the graph horizontally 2 units, left or right? Right. So this is a left shift by 2. And I know what that does. So I know what to do to the graph. This thing up here, I don't know what that does. It's not a transformation. It gives you the same looking thing, but nobody can graph that correctly. You can graph this correctly. All right. All right. So only two steps. It only takes 2 steps to transform e to the x into e to the 2 minus x. But it takes thought. It takes thought. Right? So what are my graphs look like here? I'm going to start with y equals e to the x. That's going to be like that, right? This is graph number 1. And just for completeness sake, I won't take off if you don't have the asymptote marked on your practice. This is kind of the practice graph. I will take off if you don't have the asymptotes dashed in on your final graph. Right? So this right here is, right there is 1. Okay? How do I know it slopes up? Because my base is E, and E is 2.72 and change. And that's bigger than 1. Since the base is bigger than 1, it slopes right. I'm sorry, up. Second, e to the negative x. That's a reflection. So that takes that blue graph and it reflects it. And now the positive x-axis is a asymptote of that. That is graph number 2. Notice it goes through the same y-intercept. Now we're going to move that buzzard over 2. So the horizontal asymptote does not change. It's going to remain the positive x-axis. What is going to change, for example, that point right there is going to move over 2. So now on this graph, I have this point right here. And that point is what? That is the point 2, 1. Okay? And my graph doesn't go up high enough, but my final graph is going to look like this. All right. I'm actually going to move that down a little bit. All right. Move the whole thing down. I know you can't do this on your graph, but your paper. But what I want to emphasize is up here, you're going to have another intercept right here, right? What is that intercept? Y-intercept. How do you get the y-intercept of any function in the universe? Plug in 0. So if I plug 0 in my function, I get e to the 2 minus 0. So this point up here is e squared, or around 7.38 if you look at the other slide. We did e squared a couple slides ago. You don't have to put that there, the number. But e squared you can. So that is our graph. It has the same horizontal asymptote. Because when you shift to the right, you just shift along that asymptote. Any questions? These transformation principles we've been through a number of times, right? If you don't have them, go back and get them. If you didn't do well in chapter 1 test, 1 and 2, that was probably part of what you didn't do well on. Okay, one more. Oh, there's our laws of exponents. Next slide. That's a summary that I kind of compiled through together, right? Graph, that buzzer. All right. How do you always start? A plan. What's the first step in your plan? Start with a function whose graph you know. Start with a function whose graph you know, which is usually from the library of functions. So we're going to start with y equals e to the x. The library of functions. All right. We have to transform that into this. Now, my Poissonal preference doesn't have to be yours. Let's identify this stuff here. The 3 is going to be what kind of transformation? The 3? If it were multiplied, it would be a stretch or compression. But if it's added, it's up. Vertical up. Right. Now, speaking of, this negative right here is going to do what to the e? It's going to reflect it about the x-axis. X plus 2 is going to be a shift horizontal left. So that's important. You do enough of these transformation problems to work enough with transformations that you can read those things off in a simple problem like this. All right, so my first choice, my preference, I would leave the 3 to last. It's easy to take your graph at the end and just move it up. But when you've moved it up, you got to be really good to start reflecting it and stuff, right? So I leave my shifts to last. I do my compressions and my reflections first. Okay? So I'm going to start off with y equals e to the x. I'm going to do that negative. Now keep in mind, that's a substitution. And it is going to be a reflection about. Oh, wait a minute. Whoa, 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 whoa. What am I doing? What am I doing? Sorry. Typo. That's an X. The negative goes there. Reflection about the x-axis. The negative goes up front. Number two. Oh, that's number two. Number three. We're going to do this exponent up here. X plus 2 is a substitution. So I'm going to do y equals minus e x plus 2. That is a shift left 2. Counterintuitive. Substitutions are usually horizontal. They are counterintuitive in that they move, x plus 2 moves in the negative direction. Right? Don't you wish you had classes that got out 25 minutes? Oh, well, you probably do, just not this one, right? Yes, sir.
Like the last one, like you don't got to do like the negative, like put the negative in front. Like
this?
Last, yeah.
You say I don't have to do that here?
Yeah, you don't have to do that.
Mm-hmm. Because we don't have that up here. If that were x, if that were 2 minus x, then you have to do it. But x plus 2 or x minus 2, no. And then the next step is I just add a 3, right? So 4, I'm going to do y equals minus e, x plus 2 plus 3, which is the same as putting it up front, right? But I like to tack it on the end just to make it the same form. And that is a shift up 3. You start with y equals e to the x. And let's do our, okay. And this point here is 1. Then we reflect about the x-axis. That makes it go, and this right here is negative 1. Still the same horizontal asymptote because it's the x-axis. This is graph number 1. Always number your graphs. Graph number 1, graph number 2. Next, oh, I usually make those different colors. Here's what we're going to do. What are we going to do right here? All right. Let's make that something that doesn't get much love. How about pink? Ooh, that's too pink. How about that color? There we go. Pumpkin. That's pumpkin. Pumpkin spice. What do you think? Right? The cheapest pumpkin spice you'll ever get. Right? So the next one is going to be shift left 2. So this gets shifted this way 2. So that minus 1 y-intercept goes to here. And that becomes what point? Minus 2 minus 1. And it's going to go like this. Right? And what is this point here now? Well, plug in 0. If I plug in 0, I get e to the minus e to the 0 plus 2. That's minus e squared. And so this right here is going to be roughly minus 7.38, right? That intercept, right? Or which is minus e squared. That's what you put, minus e squared. But just to give you an idea how far down that is. Now, I don't care if this is to scale on your graph, as long as you have stuff labeled. Labels cover a multitude of sins, right? You don't have to be a Leonardo da Vinci here. Last one, we're going to shift this whole thing up 3. Kafo, kasafo. everything goes up 3. The asymptote goes up 3. So let's start there. The asymptote goes up to 3. This point here goes up 3. So that's going to be right there. That's the point. -2, 2. The y-intercept goes up 3. Now, it's still going to be negative, right? Because if it's negative 7.38, roughly, it goes up 3, it's going to be negative 4 something, right? So it's going to be like up here. And that's going to be like 4 minus e squared. And so what does my graph look like? Oh, over here, sorry. Over here on the left, this is also this is graph 3 right here. This right here is graph 4. And that's our final answer. And then if you look down here, this was obviously on the calculator. You can check your answers on your calculator. Now keep in mind, if you have a calculator section of the test, you should do that. How come in the homeworks, I often say, check your answers on your calculator? I don't even give you the answer. If I say graph this, you should be able to graph it on your calculator and have them match. If they don't match, one or the other is incorrect. Maybe both. Right? Any questions on this guy? Same procedure. You start with something from your library of functions. We're studying exponential functions now, so that's e to the x. That could be 2 to the x or 1/2 to the x or what have you. You do your transformations that we've done all semester. You start with the function whose graph you know, which was this blue graph, and you work it into the function whose graph you don't know. By the way, if you can do this in your head, I still want to see some work. I can't do it in my head. So if you have that much acumen, right, just amuse us mortals and throw down a little bit of work. All right, laws of exponents. I'm not going to go through these. This is kind of a table you should have in your notes. And you need to know these, know how to work with them. Especially the rest of this chapter. This chapter deals and involves a lot of exponents. A lot of exponents. Very common mistake. Hear, O Israel, the Lord our God is one. The most common mistake in algebra is, I've shown this to a lot of algebra teachers, and I've had nobody tell me that there's a more common one. Put that way. The most common mistake in algebra, while we're on the subject of rules of exponents, you cannot distribute the exponent over addition or subtraction. You cannot distribute the exponent over addition or subtraction. You do distribute the exponent over multiplication and division, which is right here. Over multiplication, you distribute the exponent over multiplication. And I can explain why too. You kind of distribute it here over division, but not if there's a plus in the middle or a minus, right? So this is also not true. If it's a minus there, it doesn't equal that. The second mistake is likened unto it. And this is so tempting to do. Calculus students do this all the time. They've had a lot of math. This is distributing, because all this is, ladies and gentlemen, is that equals this. And so all you've done here is to distribute the 1/2 to the a squared and get a, 1/2 to the b squared and get b. Doesn't work. I see it all the time. However, over here, look here. Actually, I don't have it here. Well, I'm going to add one then. We're going to add one here, right? The nth root of AB equals the nth root of A times the nth root of B. That is true. You can distribute over multiplication. This is really an extension of this. That is really the same as this. You can do that, but you can't do it if there's a plus in the middle. All right, solving exponential equations. These are different kinds of equations. If you don't practice these, like most things in this class, but especially this topic, if you don't practice these, ain't gonna end well. Do lots of these. Do these till you can do them fluently. A little theorem here. Equal basis means equal exponents. What does that mean? If I have a to the s equals a to the t, which is right here, that means since the base is the same, the exponents have to be. Right? If I get 2 to the pig equals 2 to the cow, 2 to whatever it is, pig, equals 2 to whatever else cow, then pig has to equal cow. A to the s equals a to the t means s equals t. It's almost as if, math departments around the country are getting nauseous right now. Carl Gauss, Isaac Newton, forgive me. It's almost as if you can cancel these. Oh, I gotta erase that. Oh, real mathematicians would hate that. But it's almost as if the A's are the same, you can cancel them. I didn't say that. Oh, I'm sorry, Archimedes. And the archangel of mathematics. I have to apologize to the, oh dear. Okay, so let's use this. Let's use this. Look at this. This is called an exponential equation. Why is it an exponential equation? Because what you're solving for, x is in the exponent. You have x up here. Yeah. Right? The weapon we're going to use for now, and we're going to get more sophisticated tools coming up, is we're going to use this equal exponent. Equal basis means equal exponents, right? So let's see how that works. I got 4 to a power and 32. Now you can picture if you want 32 to a power. It's to 1 maybe, okay? But these are not the same basis. So you can't go x minus 1 equals 1. Everyone see that? You can't go x minus 1 equals 1 because they are not the same basis. I need to get the same base. Question. What power do I have to raise 4 to get 32? 4 times 4 is 16. Times 4 again, which is 4 to the third, is 64. Yeah, it's around 3. 4 to the 2 is 16. 4 to the 3 is 64. So it's going to be between 2 and 3. It turns out you're right. It's going to be 2.5. How did you get that? Guess? No, I don't think you guessed. You're pretty good at this. Oh, 32 is half of 6. That's interesting. That's interesting. Okay. All right. Well, he's right. But okay, here's what we're going to do. We're going to make them the same base. They aren't the same base. We're going to make them the same base. 4 and 32 are both powers of what? 2. Ergo. Okay. Well, actually, let me. Four is 2 to the 2. 32 is 2 to the 5th. Same base. We're not out of the woods yet. We're not out of the woods. The right side, I still have 2 to the 5th. The left side, what does this equal? Pop quiz. I didn't tell you about pop. I don't do enough pop quizzes. Write down on your paper, every one of you, how do you combine those exponents on the left? How do you combine those exponents? Use the chart a couple pages earlier if you have to. You're going to use the property that a to the s to the t equals a to the st. You need to be able to do this. So 2 to the 2 to the x minus 1 is 2 to the 2 times x minus 1. You multiply those. Now, the student will observe. We have equal bases. So I'm only going to write this once. Equal bases means equal exponents. So if the bases are the same, the exponents have to be. I get rid of the bases. It's almost as if you could cancel them. Now, look what that did. That got my x out of the exponent. How do you pry the x out of an exponent? This is how. Well, this is one way. So now, 2x minus 2 equals 5. By the way, Mike was right. Look, the exponent's x minus 1. So you see from this last step, 2 times the x minus 1 in parentheses, you see that x minus 1 has to equal 2.5. 2 times 2.5 is 5. But we're going to distribute that, 2x minus 2. So that's going to be 2x equals 7. X equals 7 over 2. Yeah. This is another one. There's nobody I trust that can do that in their head. All right. If you come up with just that answer on a test without support, I'm going to want to see that ability demonstrated in front of me. I'm going to want to see that. Okay. You're going to have some. Now, I can understand somebody maybe doing fewer steps if they were good, but to go from there to there, I want to see that. Okay. Now, the student will observe. If we take the calculator on here on the right, you take y equals 4 to the x minus 1 and the 32. The x coordinate at the point they intersect is 3.5. So you can check this on your calculator. If you're given this on the calculator part of your test, you can check it. All right, so the key here, ladies and gentlemen, is to work this work into a form where there's the same base on each side. You're not starting with the same base. And by the way, this is not like an introductory problem. Why are we getting in class first? Because we've done some of this material, and secondly, you get an explanation here. The book has some simpler ones, right? I don't I don't feel usually obligated to parrot the book, although I do follow the books for you, right? But the key step here is this stuff in red. You work the problem into where you have the same base on each side, and then you set the exponents equal. That's the key. How about this guy? Well, the good news is you kind of got the same base everywhere, E. That's good news. All right, well, what is the left side? Go back to this property right here, in fact. E to the x is E to the x squared. Now, this one may take a little more work, but if you know, a little more thought, it doesn't take any more work. If you know your properties of exponents right here, by the way, all these work in both directions. The left side equals the right side, but don't forget the right side also equals the left. So in our current problem, we have e to one power divided by e to another power. That's this. But also, e to one power divided by e to another power, I subtract the exponents. So here, I'm going to subtract the exponents. This equals e to the x minus the exponent at the bottom, minus 2. Yeah. And so that's going to be e to the x squared equals e to the x plus 2. Equal bases, equal exponents. X squared will then be x plus 2. So we got the x out of the exponent. Our problem here, part of the problem, was that we had our unknown for which we were solving in the exponent. We got to get it out of the exponent. So this means x squared minus x minus 2 equals 0. Quadratic. We know 12 ways of solving a quadratic, right? This one, I think, factors. What? X minus 2, x plus 1. X minus 2 equals 0. X plus 1 equals 0. X equals 2. X equals minus 1. The good news is you can check your answer here. You could take the 2. If you put 2 in here, you get e to the 2 to the 2. That's e to the 4, right? Over here, you have e to the 2 divided by e to the minus 2. That's going to give you e to the 2 minus a minus 2. That's e to the 2 plus 2, which is e to the 4 on the right. And the same thing happens with minus 1. All right, so you can check your answers a lot of times on these. Here's some homework for next time, and we'll end it there. All right? We'll end it there. All right? Have a safe weekend. Do something fun. Yes, sir.
This one doesn't do it.
Okay, okay. All right.
I want to know about the.
Okay. Okay. All right. Let's. I'll be with you momentarily. Let me save my work here. Put on your schedule Spark for Monday night, right? All right, we're only going to do a couple more sections in this chapter, by the way. And then the rest of it's going to be after, we're going to go to chapter 5. And then the rest of it's going to be after break. Right? What you do know after break, there is class after break. I heard the other day someone says, oh, there's class after break? Yeah, it's 2 weeks. I know all of you guys know it, right? You guys are too bright not to know that. Right? Some people are like, oh, there's class after break. See ya.